Bringing external reality onto a trustless ledger creates an immediate point of friction. Smart contracts require mathematical proof before executing a payout. However, institutional participants entering complex prediction markets must protect their specific odds, exposure limits, and proprietary modeling logic. These two requirements, public verifiability and strict privacy, are inherently opposed. Executing on a standard public EVM forces participants to publish their exact position. The ledger guarantees payout, but broadcasts the strategy for the rest of the market to copy. A fully transparent settlement destroys the commercial advantage of the participant. Traditional smart contracts enforce an unacceptable binary choice between cryptographic verifiability and data privacy, rendering standard architectures unviable for high-stakes prediction markets. PredictResolve is an architectural solution designed to eliminate this exact compromise. It solves the paradox by physically decoupling the computation of the prediction result from the on-chain enforcement of the actual payout. The architecture relies on a four-step framework: predict, verify, resolve, settle. To map this out, we track two mutually exclusive data streams, one carrying fully encrypted private terms, the other carrying publicly verified event data. The objective is clear: execute an exact FXRP settlement on the blockchain without the enforcing smart contract ever reading the initial odds or proprietary conditions. Looking at the architectural diagram, we start with the first data stream in the far left column, the participant's initial position. The participant generates specific private inputs. This includes the chosen prediction, the exact FXRP stake size, and the required payout odds. These fields are locked down with encryption on the user's client device before the data ever leaves their possession. Because of this end-to-end encryption, the specific terms are never broadcast to the public EVM, eliminating the threat of front-running. Securing the user's position covers the private requirement, but the system still needs an objective trigger from the external world to process the contract. The proprietary strategy is completely firewalled off from the public chain from the point of origin. We pivot to the second data stream in the adjacent blue panel, acquiring the external event outcome. The architecture relies on Flare Decentralized Connectors, or FDC, to ingest public Web2 data without depending on subjective human oracles. A finalized result is pulled directly from a whitelisted Web2 API source and routed into the Flare ecosystem. Using the Web2 JSON module, the system generates a cryptographic attestation of that exact API response, locking it as an immutable record. An AI module evaluates this response to normalize formatting and flag any conflicting evidence across multiple external APIs. The AI layer evaluates data formatting. It does not calculate payouts, and it has absolutely zero authority over the underlying funds. The pipeline now holds a mathematically verified external real-world outcome, perfectly prepared for evaluation against the user's encrypted private terms. This creates the central architectural challenge. How do encrypted private terms and public verified data interact without leaking proprietary information? The solution operates in the Flare confidential compute layer, utilizing a secure hardware enclave known as a trusted execution environment. Both distinct data streams converge exclusively inside this specific enclave. Inside the TEE, the private terms are securely decrypted in isolation. The terms are compared against the FDC verified outcome, and the specific win-loss conditions are calculated deterministically. The exact parameters of the calculation are dropped. The only data exiting the enclave is a single payload declaring the win or loss status and the final FXRP payout amount. This division separates the logic from the capital. The TEE computes. The contract enforces. The TEE hardware never touches the underlying FXRP. The enclave functions as a cryptographic black box, allowing deterministic execution of complex rules, while perfectly shielding the proprietary inputs from the settlement layer. Moving to the yellow panel, we address the final trust gap. Allowing an EVM smart contract to safely enforce an off-chain calculation it is not allowed to audit. The system generates a trust receipt, a cryptographic provenance record produced by the TEE. It packages verifiable metadata, anchoring the event ID alongside FDC and TEE attestation references. Stake sizing, positions, and odds are entirely omitted, permanently masked from the on-chain record. The trust receipt serves as a secure one-way filter. It provides mathematical proof to the network that the computation was valid without exposing the underlying variables that produced it. The data finally reaches the enforcement layer, where the financial consequence is executed. The smart contract ingests the trust receipt and strictly validates all FDC and TEE cryptographic signatures. Once the conditions are mathematically satisfied, the contract authorizes the programmable FXRP transfer directly on-chain. Tracing the pipeline, the decoupling holds from initial input to final ledger state. Because the computation logic and data sources are modular, the architecture scales across industries. The exact same infrastructure resolves sports predictions, verifies weather thresholds, and calculates financial election events. Private strategy stays private. The external result becomes verifiable. PredictResolve turns a private prediction into a highly verifiable, confidentially resolved, and enforceable settlement. Predict, verify, resolve, settle.